A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. You are standing on a balcony in the middle of the night. The air is still, maybe a bit humid, and then suddenly the entire sky flashes a brilliant artificial white. You count. 1, 2, 3. You're waiting for the roar, the physical shake that tells you how close that was. But nothing happens. 10 seconds pass. 30 seconds. You start to think maybe it was just a power transformer blowing out, or a silent technical glitch in the clouds. Then, just as you're about to head back inside, a massive window-rattling thud rolls over the building. It's disorienting, right? Your brain wants to connect the light and the sound into one event, but physics has other plans.
It's the ultimate sensory mismatch. People living in high-tension areas, especially with the current escalations between Iran and Israel, are dealing with this daily. You see a light, you hear a sound, and your primate brain shouts, "Danger right here," when in reality that event might have happened 60 miles away and 5 minutes ago. I'm Herman Poppleberry, and today we are stripping away the illusion of the overhead explosion.
Today's prompt from Daniel is about exactly that, the physics of sound and light latency in conflict zones. Daniel's been living through this, and he's noticed that what looks like the present is actually the past. It's a bit like stargazing, where the light you see from a star left its surface years ago. In a war zone, the star is a ballistic missile intercept, and the years are converted into seconds or minutes of acoustic delay. By the way, today's episode is powered by Google Gemini 3 Flash, which is helping us parse through the fluid dynamics and atmospheric science behind these weird prompts.
It's a fascinating prompt because it touches on something so visceral. We rely on our senses for survival. If you hear a twig snap behind you, you turn around. But when the twig is a 3-ton interceptor rocket hitting a target in the exosphere, your senses are actually the worst guides you could have. We're going to break down why the atmosphere is essentially a giant distorting lens and a very slow delivery service for information.
The core of this is the light-sound gap, which sounds like a bad indie band, but is actually just the brutal reality of physics. Light is basically instantaneous for anything happening on Earth. At 300,000 kilometers per second, if an intercept happens over the border, you see it the moment it happens. But sound is a slowpoke.
It really is. At sea level, sound moves at about 343 meters per second. To put that in perspective for everyone listening, that is roughly 1 kilometer every 3 seconds. Or, if you prefer miles, it's about 5 seconds per mile. So, if you see a flash and the boom takes 30 seconds to reach you, that intercept happened 10 kilometers away. That's a decent distance, but it feels incredibly close because the visual was so intense.
But Daniel mentions something even crazier. Sometimes you see something that looks directly overhead, but it's actually hundreds of miles away. How does the visual side lie to us that badly? I get that sound is slow, but shouldn't my eyes at least tell me where the thing is?
You'd think so, but we suffer from a massive parallax error. Our eyes are about 6 centimeters apart. That's great for judging if a coffee cup is within reach, but it's useless for judging distance against a featureless black sky. When you look at an explosion at 30 kilometers altitude, which is where systems like the Arrow 3 operate, there are no reference points, no trees, no buildings, no clouds to give you scale. A massive explosion 50 miles away looks identical to a small one 5 miles away.
Right. It's like looking at a plane at night. You see the blinking lights, and it looks like it's just skimming the rooftops, but then you realize it's at 30,000 feet. But with a missile intercept, you also have the curvature of the Earth playing tricks on you.
That's a huge factor. Because these interceptions happen so high up, sometimes literally in the exosphere, they are visible from incredible distances. If an intercept happens at a high enough altitude, someone in Tel Aviv and someone in Amman might both swear the event was directly over their house. In reality, it was somewhere in between, or even way out over the desert. The light travels in a straight line, but because the Earth curves beneath it, the angle at which you see it makes it feel like it's looming over you.
And then there's the sound delay for those high altitude ones. If an arrow 3 hits a target at an altitude of 40 kilometers, even if it is directly above your head, the sound has to travel through 40 kilometers of air. If we use our 3 seconds per kilometer rule, that's 120 seconds. 2 full minutes.
And it's actually longer than that. This is where the physics gets really nerdy. The speed of sound isn't a constant 343 meters per second. It depends heavily on temperature and air density. As you go up into the atmosphere, the temperature usually drops, at least until you hit the stratosphere. Cold air is slower for sound. So that boom from 40 kilometers up is actually trudging through freezing thin air, which delays it even further. By the time you hear it, you might have already finished your cup of tea and forgotten about the flash you saw.
That creates a ghost event feeling. You hear a sound and you're looking for the cause, but the cause is already gone. The debris might have already fallen into the sea by the time the acoustic report of the impact hits your eardrums. I want to talk about the double thud, though. People often report hearing 2 distinct bangs. Is that the interceptor and the target, or something else?
It's usually a mix of things. Sometimes it is the launch of the interceptor followed by the later explosion of the target, but often what you're hearing is a sonic boom. Most modern interceptors, like the ones used in the Iron Dome or David's Sling, are supersonic. They're moving faster than the speed of sound. So, as the missile streaks across the sky toward its target, it's dragging a cone of high-pressure air behind it, a literal shockwave.
So the boom I hear might not even be an explosion. It could just be the missile itself saying hello as it passes by.
And because the missile is moving toward the target and away from the launcher, the sequence of sounds gets jumbled. If you are standing near the target area, you might hear the bang of the interception first, and then the whoosh of the interceptor's engine arriving a second later, even though the engine was running long before the hit. It's like a movie where the audio track is out of sync.
That sounds like a nightmare for situational awareness. If you're trying to figure out if you're in danger, and the sound is lying to you about the timing, and your eyes are lying to you about the distance, what are you supposed to do?
Well, that's why the flash-to-bang method is so vital. It's the only objective data point you have. If you see the flash, you start counting immediately. If the sound arrives in under 5 seconds, you are very close to the event, less than 2 kilometers. If you get to 30 seconds, that thing was 10 kilometers away. If you get to 100 seconds, it's 40 kilometers away. Knowing that distance can take the panic out of the situation. A boom that takes a minute to arrive is mathematically incapable of being on top of you in the way people fear.
But what about those window rattlers? Sometimes you don't hear a sharp crack, but the whole house shakes. I've heard people say the windows rattled, but there was no sound. How does that work? Is that some kind of stealth explosion?
That's infrasound and low-frequency energy. High-frequency sounds, the sharp cracks and pops are easily absorbed by the atmosphere and blocked by buildings. But low-frequency energy travels incredibly well over long distances. It's the same reason you can hear the bass from a car stereo 3 blocks away but not the lyrics. A massive explosion, like a ballistic missile warhead being neutralized, releases a huge amount of low-frequency pressure. That pressure wave can travel 100 miles, rolling over the terrain. It has enough physical energy to flex a pane of glass, but the frequency is so low it's at the very edge of human hearing. So you feel the explosion before, or instead of, hearing it.
It's like the atmosphere is acting as a filter, stripping away the noise and just leaving the raw punch. You mentioned something in our prep about atmospheric inversion, too. That sounds like it could make a distant bang sound like it's right next door.
Inversions are wild. Normally, air gets cooler as you go higher. But sometimes, especially at night in desert regions like Israel or Iran, you get a layer of warm air sitting on top of a layer of cool air near the ground. Sound waves usually travel upward and dissipate into space, but when they hit that warm layer, they can actually refract or bend back down toward the Earth. It's like the sky becomes a mirror for sound. A boom from a different city can bounce off the atmosphere and land right in your backyard.
So you're telling me I could be in Jerusalem, Hearing a boom that actually happened over the Mediterranean because the atmosphere pulled a bank shot with the sound waves.
Literally. It's called ducting. The sound gets trapped in that cool layer near the ground and can travel hundreds of kilometers with very little loss in volume. This is why people get so confused. They hear a loud, clear explosion and assume it's local, but it's actually a refined sound that's been channeled from halfway across the country.
This really reframes the whole experience of being in a conflict zone. It's not just scary, it's a physics puzzle you're forced to solve in real time. I want to dig into the visual side a bit more though. Daniel mentioned the star effect. When I look at a missile intercept, it often looks like it's hovering. It's this bright point of light that doesn't seem to be moving, and then, boom, it vanishes or explodes. Why does it look stationary if it's moving at Mach 5?
That's all about angular velocity. Imagine you're standing on a train track and a train is coming straight at you. From your perspective, the train doesn't look like it's moving left or right, it just gets slightly larger. In the sky, if an interceptor or a missile is heading on a path that is even remotely toward you, its lateral movement across your field of vision is zero. Because it's so far away, you can't perceive it getting larger until the very last second, so it appears to be a fixed star.
And then, if it's traveling at a shallow angle at a very high altitude, it's like a plane on the horizon. It looks like it's barely crawling, even though it's covering kilometers every second.
And because there's no air resistance to create a trail. In the upper atmosphere, no contrails or smoke once you get high enough, you lose all the visual cues of speed. You just see a light. This is why people think they're seeing UFOs or hovering weapons. It's just high-altitude physics playing tricks on your depth perception.
So, let's summarize the lies our senses tell us. Lie number 1. If I see it above me, it is above me. Reality, it's likely miles away at a high angle. Lie number 2. The boom happened when the flash happened. Reality, the boom is a delayed courier. Lie number 3. A loud boom means a close explosion. Reality, it could be a sonic boom or an atmospheric inversion.
And lie number 4. I can tell how big it was by how bright it was. Atmospheric conditions like humidity or dust can scatter light, making a small interceptor self-destruct look like a massive tactical event.
So, how do we actually use this? If I'm Daniel and I'm hearing these things, what's the hierarchy of reliability? I assume the official alerts are first, but if I'm just looking out the window, what's the smartest way to process that data?
The flash to bang is your gold standard. It's physics. It doesn't care about your feelings or the news. If you see a flash, count. If you get to 60 and then hear the boom, you can relax a bit. That event was 20 kilometers away. It wasn't over your house. Another trick is the window test. If your windows rattle but you don't hear a sharp crack, you're likely dealing with a very distant, very large event. The high frequencies died out miles ago, leaving only the house-shaking rumble.
What about the color of the flash? Does that tell us anything? I've seen some intercepts that are bright green, some that are orange, some that are pure white. Is that just different types of fuel, or is there something else going on?
It's actually chemistry. The color of the flash can tell you what's burning. A bright clinical white is often the magnesium or aluminum used in solid rocket fuels. An orange or reddish glow might be more traditional high explosives or liquid fuel. Sometimes you'll see a blue or green tint, which can be the result of specific metals in the warhead or even the ionization of the air itself if the energy release is high enough. But again, don't rely on it too much. Atmospheric haze can turn a white light yellow very quickly.
It's wild that we're talking about this as a practical guide. It's a somber reality, but understanding the science really does strip away that layer of unknown terror. If you know that the sound is just a slow traveler, you aren't as shocked when it arrives 2 minutes late.
Knowledge is a shock absorber. When you understand that the atmosphere is a chaotic medium, you stop trying to find a one-to-one correlation between what you see and what you hear. You start treating the sky like a data field.
I want to talk about the sonic boom versus explosion distinction again, because I think people miss this. If an Iron Dome battery fires, you hear a series of pops as they leave the launcher. But then, as they accelerate, you might hear a much louder crack. That's the missile breaking the sound barrier, right?
Yes, and that crack can be incredibly loud. It's a continuous shock wave that follows the missile. So if the missile is flying a path that parallels your position, you're essentially standing under a carpet of sound. It's not a single point source like an explosion, it's a line source. That's why some booms sound long or rolling while others are a single sharp thud. A rolling boom is often a sonic boom or a moving shock wave, whereas a sharp thud is more likely the actual kinetic impact of two objects meeting.
So a sharp sound is the actual business end of the intercept. That's the success sound, usually.
Usually. But even then, at the altitudes we are talking about for ballistic defense, like the stuff coming from Iran, the kinetic, sound is often lost. What you hear is the pressure wave from the propellant or the warhead's chemical energy. At 60 kilometers up, there isn't enough air to even carry a sound in the traditional sense. The sound has to wait until the pressure wave hits the denser parts of the atmosphere to actually become an acoustic wave we can hear.
Wait, so there's a dead zone? Like if an intercept happens high enough, it's silent?
Effectively, yes. In the near vacuum of the upper atmosphere, sound can't propagate. The energy has to travel as a shock wave, a physical displacement of particles, until it hits the thick air of the stratosphere. Only then does it convert into the sound we recognize. This is why high-altitude intercepts have such a weird, muffled, thumping quality. They aren't loud in the way a firecracker is loud, they are heavy.
Heavy is a great word for it. It's a weight in the air. I think that's what Daniel was getting at with the stars analogy. The sky is full of these heavy events, but they are all lagging behind reality.
And you have to consider the jumble effect. If multiple intercepts are happening, the sounds are all arriving at different times based on their specific distances. You might see 3 flashes in 5 seconds, but hear the booms over the course of 3 minutes. The first flash might be the furthest away, so its boom arrives last. Your brain tries to pair the first boom with the first flash, but you're actually pairing the first boom with the third flash. It's a complete scramble of cause and effect.
It's like a cosmic shell game where the shells are made of light and the P is a sound wave. I'm thinking about the practical side for people on the ground. We talked about the flash to bang and the window test. Is there anything else? Like looking at the debris or the smoke trails.
Smoke trails, or contrails, are actually very useful for judging distance. If you see a trail and it looks wavy or broken, that's usually due to high altitude winds. If the trail is very thin and sharp, it's likely closer to you. Also, notice the expansion of the cloud. A cloud of debris from an intercept expands at a known rate. If it looks like it's growing slowly, it's because it's massive and very far away. If it expands and dissipates in seconds, it's much smaller and closer.
That's a good one. It's all about scale. If you see a puff that looks like a dandelion, but it stays in the sky for 10 minutes, that puff is actually a kilometer wide and sitting in the jet stream.
It's all about training your brain to reject its first instinct. Your instinct says, that's a small light above me. Your physics brain should say, that's a massive energy release 40 miles away.
I think we've really hammered home how unreliable our senses are. But I want to pivot a bit to why this matters for the alert systems. We have these apps and sirens, and people often complain that the siren goes off after they see the flash, or sometimes before they hear anything. Based on what we've talked about, that's actually exactly how it should work, right?
It's the only way it can work. The radar systems see the missile at the speed of light, or rather, the radio waves travel at the speed of light. The computer calculates the trajectory in milliseconds. The alert is sent out via fiber optics and cellular networks at, again, nearly the speed of light. So the alert system is faster than the sound of the explosion, but it's slower than the light of the explosion.
So the sequence for a perfect intercept should be flash, then alert, then boom.
Precisely. If you hear the boom before the alert, that usually means the event was so close that the processing time of the computer took longer than the sound's travel time. That's when you know you're in the danger zone. But for most long-range intercepts, you get that beautiful, albeit terrifying, window of time where the light has told you what happened, the phone has told you where it is, and the sound is still on its way.
It's a weirdly polite way for physics to work. It gives you a head start. I want to talk about how this changes with the weather, though. Daniel lives in Jerusalem, which has some serious hills and valleys. Does the topography change the flash-to-bang logic?
Topography is the chaos factor. Sound reflects off hills. In a city like Jerusalem, a boom can bounce off a limestone hillside and hit you from behind. You might think the explosion happened to your north because that's where the sound came from, but the flash was in the south. The sound just took the scenic route through the valleys. This is why you should never trust your ears for direction in a mountainous or urban environment. Always trust the flash. Light doesn't bounce around corners in the same way sound does.
So, eyes on the flash, ignore the splash of sound when it comes to direction.
I like that. Eyes on the flash, ignore the splash. And remember that humidity plays a role too. In very humid air, sound travels slightly faster and carries further. On a very dry, crisp night, the sound might be sharper but dissipate more quickly. It's why some nights the booms sound closer, even if they are at the exact same distance as the night before.
Let's talk about the aha moments for people. What's the one thing most people get wrong about this?
The biggest misconception is that the loudest boom is the most dangerous one. As we've discussed, a massive, non-threatening intercept 40 kilometers up can produce a terrifying low-frequency rumble that shakes the whole city. Meanwhile, a much smaller, much more dangerous piece of debris falling nearby might only make a small whirring or smacking sound. People tend to equate volume with threat level, but in the world of high-altitude physics, volume is often just a function of how much energy was released in a safe place.
Right. A successful intercept is a huge explosion of energy. That's what makes the noise. If the missile just hit the ground, it might actually be quieter from a distance than the mid-air destruction of its fuel tank and warhead.
A quiet night isn't necessarily a safe night, and a noisy night is often a sign that the defense systems are doing their job perfectly. The boom is the sound of the defense working.
That's a really helpful way to frame it, especially for people trying to sleep through this. I want to touch on the future tech side too. We're seeing more AI integration in these alert systems. Do you think we'll ever get to a point where our phones can translate the sound for us? Like, that boom you just heard was an Arrow 3 intercept 60 kilometers away.
We're almost there. There are already acoustic sensor networks being used in some conflict zones that do exactly that. They use multilateration, the same way GPS works, but with sound. If you have 4 microphones across a city, they all hear the boom at slightly different times. An AI can take those millisecond differences and triangulate the exact GPS coordinate and altitude of the explosion in real time.
So your phone could literally tell you, don't worry, that was just a bank shot off the stratosphere.
It would take the guesswork out of the flash-to-bang method, but until that's in everyone's pocket, we have to rely on the old school physics. I think Daniel's point about the stars is the most poetic way to look at it. We are living in a time-shifted reality. The now in the sky is actually the then on the ground.
It's a literal lesson in patience. You see the event, and you have to wait for the atmosphere to confirm it via acoustic mail. I think we've covered the core of the physics here: the speed gap, the parallax, the inversions, and the topography. What are the big takeaways for someone living through this?
Takeaway number 1, trust your eyes for when and where, but never for how far. Takeaway number 2, use the flash-to-bang method. It's the only way to ground your senses in reality. Takeaway number 3, don't panic at the volume of a boom. A rolling heavy rumble is often a sign of a high-altitude, successful intercept far away.
And takeaway number 4, remember that the atmosphere is a filter. If you're hearing a thud, but not a crack, you're likely safe. Use that time to breathe.
And maybe takeaway number 5, practice. You don't have to wait for a conflict. Next time there are fireworks or a thunderstorm, use the flash-to-bang method. Get a feel for how long 5 seconds actually is. It'll make you much calmer when the real thing happens.
That's a great tip. Building the muscle memory of counting. It gives your brain something to do other than panic. You're not just a victim of the noise. You're an observer of the physics.
It turns a terrifying experience into a data-gathering exercise. That shift in perspective is psychologically huge. You go from, oh no, what was that? To, okay, that was roughly 12 kilometers away, north-northwest.
It's the Herman Poppleberry approach to survival. Solve the equation and you'll feel better.
Hey, it works for me. I'd rather be a nerd with a stopwatch than a primate with a racing heart.
I think we all would. This has been a really deep dive into something that is, unfortunately, very relevant for a lot of our listeners right now. But understanding the why behind the boom is the first step in taking back control of your environment.
It really is. The sky isn't just falling, it's communicating. You just have to know how to translate the language of latency.
Well, I think that's a perfect place to wrap this one up. We've decoded the sky, debunked the overhead illusion, and hopefully given Daniel and everyone else some peace of mind, or at least some better math to do at 3 a.m.
Just remember 1 kilometer every 3 seconds. If you can remember that, you're ahead of the game.
I'll try to remember that next time I see a star moving a bit too fast. Big thanks as always to our producer Hilbert Flumingtop for keeping the audio levels from actually exploding our listeners' eardrums. And a huge thanks to Modal for providing the GPU credits that power the AI generation for this show.
This has been My Weird Prompts. We really appreciate you guys tuning in and exploring these strange corners of physics with us.
If you're finding these deep dives helpful or just entertaining, a quick review on your podcast app really does help us reach more people who might be looking for a bit of logic in the middle of the chaos.
Stay safe out there and keep those stopwatches ready.
See you in the next one. Goodbye.
Goodbye.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from sloth